Okay, next up we have, in person, we have Rocco and Amedeo, and on virtually with us we have Marco. I hope I got all your names right, but I think I did. And they are going to talk to us about chickens. I'll let you explain further than that.
Thank you really much. We're really happy to be here. I'm Rocco Modugno. I'm a graphic designer. Can you hear me? Yeah. Nice. Sorry. Oh. So yes, I'm Rocco Modugno. I'm a graphic designer. I usually work a lot with text, and I have a fetishism for patterns, as everybody here. And I'm here with two colleagues, Amedeo and Marco, that is following us online. Maybe you can get to present
That's Marco.
Each other. That's Marco. Amedeo, want to spend a few words?
I'm Amedeo. I am a product designer. The physical type of product designer, I really dislike when they call product design the stuff on the digital world, but I ended up doing it anyway. Marco instead will briefly say something about himself.
Hello, I'm Marco. Yeah, I'm in Italy now, and I'm an electronic engineer, and I think I pose a foot on the artificial intelligence train, but the other is on the ground.
So Marco, I switch now to the presentation, and Rocco starts.
So yeah, we introduce ourselves briefly. So the presentation is going to work like this. I'm doing a short introduction. Marco is giving a math foundation to our work, and then Amedeo is showing an application of this work. So I want to start from history. Everybody of you probably knows Sébastien Truchet. Is really famous for Truchet tiling and so on. Truchet tiling, let's say, became important or were well known when Truchet was working for the Canal d'Orléans, and he went in front of a church and he saw this kind of tilings here. And so he asked himself which tilings could be made with this element here. And his great idea was a new kind of approach. Combinatorial calculation was still being discovered in that period, and he decided to do a short combinatorial studies on these tiles in order to create an ordered index, and from this ordered index he was creating composition, such this one. So yeah, the approach is more or less like this. You get the modules, you create some nodes that are permutations, and then you create composition. So then there is another important monk that took his work, that is Dominique Doigt. There is no portraits of him because all his work is considered to be Truchet work, but that's not how it was. And let's say he asked himself another question. He still was interested in the qualitative characteristics of the tilings, but also in the calculation of how many tilings could be made. In order to do so, he introduced a new kind of notation. This kind of notation is based on letters. So let's say more on typography than drawing itself. So what he was doing after he associated a letter to any spatial configuration on the tile, he was combining the tiles through letters. So he was using the alphabet. The interesting thing is that in this way he was writing in order to draw. So that's what changed in terms of methodology. So he was able, let's say, just to write and figure it in his mind in this virtual space that he created how this would look like. He also introduced some generative rules that probably were present already in the work of Truchet, but he just didn't describe. So here you can see some of the configuration of his compositions. In 2023, it was demonstrated how his approach could be really interesting if united with the digital fonts, in the sense that as soon as you change one module, then you can easily change the whole tiling. So today we introduce this work that is called Count Your Chicken, so pattern generation as a matter of counting. Now, this is the first table of Sébastien Truchet. It's really interesting to notice that even if he was using a graphical method to combine everything, in this first table still also the notation of Dua was present, but was not really adopted. But there is also another kind of notation that in this case is arbitrary, and it's the number notation. So let's say we start from these numbers in order to generate the nodes and the pattern. So when we are talking about chickens from now on, we are talking about the nodes themselves. So now maybe I pass the word to Marco that could give us a math foundation about our work together.
You can share the screen now, Marco. Okay, fantastic.
Can you see and hear me? Thank you. Hello, everybody. Thanks for having me virtually here. So what we want to do is to create a robust framework to describe patterns. And so we want to handle pattern generation with a combinatorial approach by framing patterns which are permutations as numeric literals. What does it mean? Let's say we have a pattern, and in this work we focus on square tilings, so arrangement of modules in a square grid. Let's say you have this pattern. You want to associate a number to it, not in a sensible way. The first thing we do is we identify the modules. In this case, it's just two modules, so we will define a mapping to binary digits. In this sense, we then replace the module with the digits in the square grid. And of course, we unfold the grid into a string. This is really easy, but if you fix the mapping and the unfolding strategy, you can see that a pattern identifies just one number. I mean, one binary string. Of course, this process can also be done in reverse. So if you select modules, a mapping to digits, then generating the pattern is just writing a digit string, fold the string into a grid with the same rule, and replace the digits with the module. This means that by just counting, by just having a number, we can univocally identify a pattern. Of course, this binary string is the, let's say, natural way of representing a pattern made with two different modules, but we can change the base. So for having an easier name for the pattern, we can change the base maybe to the decimal one and see, for example, this pattern is the 2025 pattern of the 4x4 grid with two modules. In this way, generating a pattern is just counting them, meaning that saying a number is and the rules and setting the rules generates just the pattern that we want. What does it mean? It means that we can generate, for example, all the 4x4 square matrices, or really any other kind of pattern. So we have an easy way to generate all of them. What do we do? What we do now? We want to find some rules, catalog them, following some rules. Basically, you define an index of them. What rules? So now we are working with visual patterns, and so we focus on rules that apply to the square grid, meaning the symmetry of the square, the natural symmetry of the square. This doesn't mean this work only applies to patterns in a visual space, but of course we do a catalog of visual patterns. What does it mean? We start with say one node. We call this 4x4 grid a node, as Dominic Dua did. and we generate the related nodes by applying the subsequent symmetries of the square. So let's say we have all the rotations, we have reflection around the major axis, and as we have introduced the negation, meaning replacing the one with the other one, we can do the same with the negative and also the symmetries. So for a given node, we will identify 15 more nodes. So in our catalog, this node is associated with another 15 nodes, which form a group. But of course, it can happen, and it sometimes, and I mean, it frequently happens, that these are not univoc. So let's say the starting node is symmetric, for example, between, for example, as axial symmetry or diagonal symmetry. This will have duplicates, and so the symmetry identifies just a smaller of nodes associated with a specific node. We use this kind of reasoning. So these generate the nodes of a given set and filter based on rules to select some, like all the nodes that satisfy some properties in a given set of nodes. For example, choose the chromatic symmetric nodes, which we call like this, which are the nodes that you can obtain, that when negated and transformed with the basic symmetries, come back to the original nodes. So, for example, this and we group nodes based on the symmetries that you use to obtain the starting node. So, for example, all these nodes satisfy this constraint of being obtained with the same set of transformation when starting from the node itself. And we group nodes like this. I mean, by using these rules. And for example, so this is a way of cataloging nodes and of trying to manage the complexity when we have all the nodes in a set, like this. It's a sort of a top-down approach, let's say, meaning that we generate all the nodes, filter, and just some nodes trickle down in this group of nodes that share visual properties. We can, of course, this is just small nodes that we will use in larger and more meaningful patterns, of course. But within this schema of thinking, we can always come back to these nodes. So for example, these numbers are obviously the names assigned as we said priorly. So this notation is robust because each number identifies one pattern. It is universally available in programming languages, meaning that you all need strings, you need square matrices if you want to represent them in squares, and possibly the change of base notation to identify the nodes with a decimal or a more natural way of representing the nodes than the binary string. Of course, this is it. This identifies a framework for naming the nodes and generating them by counting. Now, my colleague Amedeo will show you, let's say, an opposite approach, which is more explorative and less top-down of this one. The word to you.
Okay. Now we go to this. Okay. That was the nerd part. Now we got chickens. they are sneaky chickens. Actually, there's only one. It's this one. We hide it in plain sight. You can find it by activating it properly. Okay, so this is the chicken counter 1.0. So we hope to be able to expand it soon, but this is it for now. It's available online. You can check it out, do whatever you want with it. If you inspect any part of the code, you will be ashamed of how I can code this. Please don't resize the page. It will be disastrous. But you can play around with it. Okay, so we have established that we have nodes with binary digits that can be expressed in squares. White, black. 16 squares means to the 16th power. It's already quite a bit of information. How do we navigate it in a smooth, tangible, easy way? Enter the product designer that wants to make stuff touchable. So we can turn modules, and immediately the identifier of our node changes. Everything we do immediately results in the pattern changing. And it's super fast, it's super intuitive how some of these properties have repercussions all again the graphics. On top of the basic node that we have defined, and I show you here, we have established a transformation set of rules that we call canons. Canons are down there. Now they are deactivated, but if we activate the first, repetition, we see that we just stack strings together, and they become slightly more interesting, not so interesting, a little bit boring at this point. Paul Hallow that yesterday presented probably would enjoy this time of always the same, but our ties are way less interesting. So we need to find a better canon. Maybe we can negate and then repeat. Maybe we can alternate and then repeat. But what if we stack the canons in some strange ways? Suddenly the complexity goes, I would not say through the roof because we stopped at 3 nestings, but there's pretty much quite a bit of possibilities here. And we could just, in the next phase, add more canon nesting. You can explore it as you want. Anything that is red plus these 2 matrices are interactable. You can randomize whatever type of output you can imagine by clicking the title, or just feel free to look around. Just one note, here to the side, you see what is actually going on to the module. So like, for example, repetition is just node, 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 node. Negative repetition is negative of the node, etc. And so on. You can always reconstruct based on the information that we have on the paper, that you can find here, what functions are being applied. Lastly, you can do something with the graphic that you created. If you click on the red dot, you actually copy the final string that you can use for whatever graphic you want. On the paper, you also find the link for the custom typeface. This is a typeface, actually. They're not rendered squares. It's a binary font with only 2 glyphs, but you can use it. And if instead you don't want to take time pasting stuff, but just switch to chicken mode, you can download chickens. Spam whatever type of pattern you like. When you find one that is good enough, you can open it. This is a normal, fantastic chicken. Actually, the outer chicken is randomized out of a few different frames of this wonderful animation that a friend of ours created. And if you want, you can join us later at 7 something for the workshop at Panke. I don't know where Panke is, but I will discover it. I have a sad news. Unfortunately, transporting an old pen plotter from the 70s from Italy to here on a plane was not really that simple. So we ended up getting stuck with a printer. We will be printing chickens anyway. You're welcome later. Thank you very much. And that was it for Chicken Counter.
Thank you. I'm excited to make patterns with chickens. So that we have time for a little break before the next session, I think we can do one question, but also, do you want the next round of speakers to start kind of coming up to test your laptops, if you could do that. Hopefully you know if you're presenting. And yeah, who has a question? Question over there. For the people on the stream.
Thank you. Firstly, that was so cool. It all looks so great. I also really like the notation idea of like just turning it into a string of digits and then turning it into this number. But I think, and correct me if I'm wrong, it sort of assumes that it's 4 by 4. This like the number. So have you thought about including the dimensions of the pattern in the notation at all? So you could like make a 8 by 8 or a 16 by 16 thing.
Yeah, I think it's a really good idea. The point is that for this generation, all what we wanted was to reduce complexity in order also to be able to control it a bit. In fact, for example, here we are just using a binary system, but actually it could be quaternary, it could be also on radix 10 and so on. But our main aim was to reduce complexity at the moment, but we completely agree that for further developments, we should for sure do that. Maybe one last thing, Amedeo forgot to tell that the beautiful animation was made by Silvia Governa, and yeah, it was a great gift by her for our project, so I just wanted to underline this. Thank you really much.
Cool, okay, another round of applause, please.